Okay, so you will get the answer as 93 millimeter. Sorry, 93 Newton per meter. Okay, so this is our experimental value 93, and by theoretical formula for the equivalent spring stiffness for series arrangement, it is 100 Newton per meter. Okay, so now I have changed the weight connected. So I have taken 1 kg, so it is 9.81. So now we will check what is the deformation. So initial value is same, it is 37.9 centimeter. So let us see what is the deformation due to 1 kg mass. So now you can observe here, this is 37.9. And this value, so this is 48.5. Okay. So 37.9 minus 48.5. So it is a 10.6 centimeter for 1 kg. So now the weight that we have selected, it is a 1 kg. So load will be 9.81 Newton. Okay. So its static deformation. So this value is 10.6 centimeter. So this is the delta, 10.6 centimeter. So K equivalent, this is equal to F upon delta. So F is 9.81 and delta value is 10.6 into 10 to the power minus 2. So this is Newton and meter. So this is 93 Newton per meter. Okay. So we don't get exact value. So, but it is near about the theoretical value by this formula 1 upon K1 plus 1 upon K2. Okay. So similarly, we can verify the answer for this parallel arrangement also. So for the parallel arrangement, we want to find out what is the equivalent stiffness. Then find out the deformation for the known mass or known weight And again, by the same formula, K equivalent is equal to F upon delta. Okay. So F means we have to multiply mass by 9.81 and delta means you have to measure the static deformation. Okay. So this is experimental method to find out the equivalent stiffness. So now we have conducted the complete experiment for series arrangement, for parallel arrangement, and for single spring. So for your write-up, so we will start from this title. Okay. On the first page, you will write M, then requirements, then setup diagram. For this is single spring. Then write the procedure. Okay. So write the procedure for both the experiments, that is to find out the stiffness and to find out the natural frequency. Then draw this observation table to find out the stiffness of that spring. Okay, don't write this formula, theoretical calculation, because this is not part of our syllabus. In the next semester, we have machine design 1 subject. Okay, so in that subject, you will learn how to find out this K stiffness, that is the design of spring. Okay, then write down this omega n calculation by selecting mass as 4 kg and K 981. Draw this observation table, and in the calculation, you should draw this waveform on the left side, that is on the blank pages. And if you don't have the blank pages, then just draw this on the ruled pages. So draw this waveform, mention this time T1, T2, okay? And then write the time period as T is equal to T2 minus T1. Then write this calculation, experimental and theoretical. Same for parallel spring system, you have to draw this diagram. Draw this observation table. And then for this series arrangement, okay? So now I will show in the industry how the stiffness is calculated of the spring, okay? So the method that we have followed, we have connected one known mass and then we have measured the deformation, okay? So this method, it is only for the educational purpose, okay? In the industry, there is a separate machine that will find out the stiffness of the spring. Okay, is the video screen visible? Okay, so in this video, you can observe how the test is carried out on the spring in the industry. So this is one compression helical spring. So this machine is quite similar to the UTM, okay? So here the spring is undergoing the compression test and then it measures the deformation and the force value. So from that deformation and corresponding force value, the software will automatically calculate the stiffness of that spring. Okay. And also this machine is used to carry out the fatigue test on that spring. That means how much cycle that spring can sustain before its failure. So you can observe this is the graph. So the y-axis, it is the force value, and x-axis, it is the deformation. It is written here. Okay. So you will get almost a straight line. So this is force versus deformation graph. So if you find out the slope of this graph or this straight line, you will get the directly K value, that is the stiffness. So in the right side, right top corner, you can observe the values. The force is 6 Newton and the deformation, it is a 0.93 millimeter. Okay. Now this is for the compression spring. For extension spring, so the test is similar to the tension test on the UTM. Is it visible? Okay, so here you can observe. So this test is to measure the stiffness for the extension springs. So you will get the similar graph. Force versus travel means it's a deformation. And here you can directly get the spring constant. So observe here. So this is the spring rate, Newton per millimeter. Okay. So this is how the spring test is carried out in the industry. So this is not test for natural frequency calculation. It is just to find out the stiffness of that spring. Okay, so is it visible to you? So in this video, you can see how the natural frequency is calculated. So this is one physical setup. Hello, is it visible to you? Okay. So in this setup, this is the mass. Okay, it is connected with the spring. So actually your system is like this. Okay. And for this system, if you want to find out the natural frequency, then experimentally, you will find out the displacement versus time graph. So it is a similar graph that we have just found out in the Inventor software. Okay, and from this graph, you can find out the natural frequency or damp natural frequency if there is a damping in the system. So actually this setup is provided with the sensors. So they are called as a accelerometer. So this accelerometer or sensors, they are mounted on the mass. And their output is given to the computer so that software will directly record the displacement and the time values. So you can observe here how the displacement is measured in this software. So this graph, so it is the displacement graph. So you will get the X versus time graph. Okay, and from this graph, you can find out the natural frequency, damp natural frequency, and even the logarithmic decrement. So here you can observe with the help of this plunger, we are giving the initial displacement. Okay, and with this initial displacement, this mass is oscillating. So you can observe this waveform. So actually this system is an underdamped system. Okay, so you have learned this underdamped system in the module 4. So this is the graph for that underdamped system. So for the underdamped system, once it is excited, it will vibrate like this. Okay, and therefore this mass, after receiving the initial displacement, it vibrates, and after some time, its displacement, it becomes zero. That is the equilibrium position. Okay. So with this process, by using these sensors and this software in the industry, the natural frequency is calculated. Okay, so this process is quite similar to the inventor simulation. Okay, so actually this vibration system, it is for the automobile vibrations, automobile suspension system. So this is the this is another setup. So actually this setup is to measure the force vibration. So you can observe this is the actual setup. Okay, so this is the mass of the automobile, and it is connected with the spring and damper. Okay, and this bottom plate, it will simulate the road profile. Okay, so shocks are transmitted from the road profile to the mass, that is a rider, through the suspension. Okay. Okay, so these are the industrial setups, industrial lab setups to determine the frequencies and the frequency. So actually with this setup, that is a force vibration, we can study the effect of various frequencies on the displacement of the mass. Okay, so we have started with the module number 5, that is the force vibration. Okay, so in that we will study what is the effect of the changing the frequency on the displacement, that is the amplitude of the mass. So this is the physical setup. Okay, how the spring and dampers, they are tested in the industry. Okay, so we will stop